Welcome back to Unit 12. In this second mini lecture, we will apply everything we know about particle physics and astronomy to give you a brief history of the universe from the Big Bang to the present. It is astounding that we are able to do this, that we as human beings can look back 13.7 billion years into the past, and as you'll see, we are able to explain everything using our current theories of physics except for the earliest tiny fraction of a second. While there's still a lot of work to do to fully understand it, the fact that we do have explanation is, in my opinion, just astounding. But before we can understand the history of the universe, we need to briefly touch on the four fundamental forces of nature. All interactions and all forces that we see in today's world are due to one of four fundamental forces. So we have two that work on the scale of atoms, the strong nuclear force and the weak nuclear force. They only work in atomic nuclei. The strong force is very powerful. It binds the nuclei of atoms together, but it only works on atomic scales. The weak nuclear force, it's one you've probably never heard of. It's a lot weaker than the strong force, hence the name, and it's responsible for certain types of radioactivity, for neutrinos. It's also maybe responsible for dark matter interactions, though we're not sure about that. It's kind of an odd force because it's not easy to understand. The remaining two forces are the ones you're probably most familiar with and the ones that we deal with every day. The electromagnetic force, which causes electrical and magnetic forces, works over long distances. Photons of light carry electromagnetic force, so when you see photons coming from a distant galaxy, that's a force coming from that distant galaxy. Electromagnetic forces can be attractive or repulsive, but they require electrical charges. If you have just neutral objects, these forces don't work. The gravitational force, it's the weakest of all four forces, but it is one of the major forces shaping the universe. And the reason is because it works over long range, like the electromagnetic force does. But unlike the electromagnetic force, it's always attractive, and every bit of matter attracts every other bit of matter. So it basically adds up on itself. One way of thinking of how the electromagnetic force is stronger than the gravitational force is static electricity. If I rub a balloon on my forehead, I can stick it to the wall, and the few electrons that my hair puts on the balloon exert enough electromagnetic force to stick the balloon to the wall, despite the fact that the gravity of the entire Earth is pulling down on that balloon. Gravity is the weakest of the forces, but yet because it is only additive and because it works over long ranges, it's the force that really shapes the universe. As we go through this, let me emphasize that you do not need to memorize or even fully understand all of these epochs of time that we're going to go through. I'll point out the most important ones. So let's begin. We have a Big Bang. There's no testable hypothesis for what caused the Big Bang, what may have been before the Big Bang, even if there is a before the Big Bang, because what we think of as time, the seconds that work on our watch, as Einstein showed us, time and space are part of the same thing, and time and space were created in the Big Bang. So before the Big Bang, time and space as we know it did not exist. So whatever it means to be before the Big Bang, whatever caused it to happen, I'm not touching that because there are no good testable scientific hypotheses for this. But immediately after the Big Bang, until 10 to the minus 43 seconds after the Big Bang, that's a 0 point, then 43 zeros and 1 second, so an infinitesimal amount of time, is what we call the Planck epoch. This is a period of time which we do not understand because our current laws of physics break down here. There are a lot of physicists who think that during this time all four forces of nature would have been combined into one. It would have been extraordinarily hot, would have been extraordinarily dense, extraordinarily energetic time. What was going on, how things interacted, we have no numerical hypotheses to make predictions yet. People are working on this. As of right now, we have no understanding of physics that would have happened during this time. So let's just skip ahead. The next bit of time, which is still a tiny infinitesimal part of a second, all the way to 10 to the minus 36 seconds after the Big Bang, so 0.36 more zeros than 1 seconds, is a time called the Grand Unification Epoch. And this would have been, the universe would have been expanding ever since the Big Bang, and as it expands, it cools. As it cooled, gravity would have split away from the other four forces. So they were all unified in the Planck epoch. It'll cool below some degree and gravity will split away. Again, this is a hypothetical. We don't have a good explanation for it yet. And gravity would have been its own force. And at this point, you would have had the three other forces, the strong and weak nuclear forces, and the electromagnetic forces still unified as one. So if you think of it in terms of a unification of cutlery, you're talking about a spoon plus a fork plus a knife, or a spade. You can Google that. These are things that are predicted but not yet tested. There are hypotheses about the grand unification. They make predictions that we haven't been able to test yet because they require far more energetic particle accelerators than we have. Or there are a few things predicted that we've never seen, like magnetic monopoles that have never been observed. Doesn't mean they don't exist, but we've just never seen one. After this grand unified theory part of the universe continues to expand up until a trillionth of a second after the Big Bang and continues to cool. And at this point, the universe cools enough that the strong force breaks away, and we get to a point where the electromagnetic and weak forces of nature are still combined into what we call the electroweak force. And this is a physics theory. It has been well tested in particle accelerators. In fact, it's just been recently that we've put the last key in place. Electroweak theory predicted the presence of the Higgs boson, which was just discovered at the Large Hadron Collider. This epoch has temperatures and densities that we can reproduce in the lab, and we have reproduced them and find that we have a theory that works very well for this time. During this time, at some point during the Planck epoch and or the Grand Unified Theory epoch and or the electroweak epoch, something happened called inflation. I'm not talking about monetary inflation, but in some ways similar to hyperinflation of money. So you know that in 1930s Germany, or more recently in modern Zimbabwe, if the government prints a lot of money, the value of money goes way down, and so you need drastically increasing denominations of bills, such as $100 billion, to buy something small, like a loaf of bread or 3 eggs. And in the very early universe, it is predicted that something called inflation happened, where the universe expanded faster than the speed of light. Now this is allowed to happen. So Einstein's theories prohibit matter from moving through space near or faster than the speed of light, but it's allowed for space itself to move at or faster than the speed of light, and the matter can just go along for the ride. This inflation would be permitted, and it solves a couple of problems that had been seen with the Big Bang theory. First of all, the universe looks smoother than it should based on the original Big Bang theory, something that your book calls the flatness problem. Just a couple slides ago, we talked about the magnetic monopoles. This takes care of that too, because during the inflationary period, the universe would have grown from smaller than the size of a proton to about the size of a pea. And while it doesn't sound like much, that's a tremendous amount of expansion. And if you project that forward into today, that would mean that any of these magnetic monopoles that are predicted but not seen, that there may only be one within several billion light years of the Earth, which would explain why we haven't seen it. The physics behind inflation, why it happened, is not well understood. There are testable predictions. The newest results seem to be holding up these predictions. The scientists working on the inflationary epoch are definitely onto something, but it's still a little nebulous as to what happened. For our purposes, it's just in a tiny fraction of a second the universe expanded by orders upon orders upon orders of magnitude, and that this solves a lot of issues in the Big Bang, and it makes predictions that have been testable. Inflation seems to be passing these tests. At the end of this electroweak epoch, a trillionth of a second after the Big Bang, the universe has cooled to a point where the electromagnetic and the weak forces decouple, and so normal particles begin to appear. And I call these normal particles because what appears are things called quarks and gluons and antimatter. And the majority of the universe is something called a quark-gluon plasma. So regular atoms don't yet exist. It's still way too hot and way too dense for protons and neutrons and atoms and electrons to exist. But there are the building blocks of those all around. Another seemingly odd thing is that matter and antimatter should exist in almost equal parts. Matter and antimatter meet and they annihilate and leave just energy. Some people will claim, well, there should have been exactly the same number of matter particles as antimatter particles, so they all should have canceled out and not left anything behind. But tests in particle accelerators, including the Large Hadron Collider, have shown that when you create this quark-gluon plasma, this phase like the universe was at a trillionth of a second after the Big Bang, 100 trillion degrees and extraordinarily dense, that for some reason there is just a tad bit more matter than antimatter. And so while we may not be able to fully explain why, we can see that this actually did happen. And so over time we'll see that the antimatter will annihilate the matter except for that little extra bit. Although this is a weird state of matter that we don't have in our everyday lives, we have been able to reproduce it in the lab, and it matches the predictions of the theories. After about a millionth of a second, the universe has cooled off so it's only 1 trillion degrees. And once you get this cool, the quarks that are zooming around can now begin to form larger particles, protons and neutrons, and the antimatter companions of these, antiprotons and antineutrons. And the matter and the antimatter begin to annihilate, leaving that tiny bit of regular matter that was extra behind. Protons and neutrons all came from this epoch up to about 1 second after the Big Bang. After 1 second, the universe cooled off enough that electrons and their antimatter companions, the positrons, began to appear and annihilate, leaving just the excess electrons behind. And this annihilation left 1 electron for every proton that formed behind too. And so the temperature continues to drop now to only 1 billion degrees, 100 seconds after the Big Bang, getting positively chilly. Most of the antimatter is now gone at this point, and we're left with mainly ordinary protons, neutrons, and electrons.